Chips in a circle. So this is another one of those problems where we're going to ask you to critique this proof. So let's get started with the problem statement. There's a circle of 15 251 chips. They're blue on one side and red on the other. Initially, all of them are on the blue side, and in one move, you can take any 4 consecutive chips and flip them over. Is it possible to get all of the chips showing red? So before we begin looking at the proof, let's first make sure we understand the problem statement. So we've got this huge circle of 15 251 blue chips. And the move we have is that we can select 4 consecutive chips. So let's say I select these 4, and I can flip all of them. And then I can say select these 4 in my next move, and flip all of them. And also there's nothing stopping me from flipping chips I've already flipped before, so I could say select these 4 consecutive chips, and flip these so that the ones that were already flipped to red become blue again, and these ones would become red. So now that we have the problem statement all set up, let's go ahead and look at this bad proof. So the proof states, no, it is not possible. Let's assume for the sake of contradiction that we did convert all 15 251 chips to red, like this. But then this must mean that in the very last move, there must have been 4 consecutive blue chips so that we could turn them red in the last move. So that looks a bit something like this. And that means the remaining 15 247 wrapping around are all red. And then in kind of an inductive way, we can look at these 15 247 and state that the last 4 of these must be blue. And then again, in an inductive way, we say the last 4 of these must be blue, 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 all the way around. And we repeat this k times all the way to k equal to 3,812. But at the very end, once we keep repeating this, wrapping all the way around the circle, we end up with 3 consecutive red chips and the rest blue. But we know we started off with all the chips blue, not 3 consecutive red chips, and our move is to turn 4 chips over, so we can't have just 3 chips left over that are red, which is a contradiction. Alright, so what's wrong with this proof? Well, there's a couple ways it could be wrong. The first way is if it says no, it's not possible, but there actually is a way it's possible. And the second way is if, yeah, it's not possible for us to turn all of them red, but something else is wrong with this proof. So take a moment, pause and think about which one of those 2 situations you think it is. Hopefully now you have some intuition that no, it is not possible, or at the very least, you weren't able to come up with a way that would make this possible, so let's roll with that. So that means this statement is correct, and there's something else wrong with the rest of this proof. So take a moment and think about what the issue is with the remaining part of this proof. Okay, so the issue is that it's assuming the method. It is giving a very particular way of trying to convert the chips to red and saying that that method doesn't work. What it's saying is that you start off with all blue, and that the way you should be trying to turn them all red is by picking 4 chips, flipping them over, then pick the next 4 consecutive chips right after those, turn those all red, and keep going all the way around using this method to try and turn all the chips to red. The issue is that the move we have is to turn 4 consecutive chips over. We don't have to pick 4 side by side. We could overlap, we could jump around the circle, there's a bunch of different things we could do. So our proof needs to tackle all the different strategies that someone could use to try and turn the circle all red. So we need to find something that works regardless of what method the person chooses to use. The proof should show no matter what they're doing, it is still not possible. Not that it's not possible for just this method. So someone could choose to start off with this blue circle, flip these ones red, and then maybe flip here, and then overlap again, and then go to the other side of the circle. But to reiterate, the proof that we come up with has to show that it's not possible, regardless of what they're doing. So let's get started. A good proof is going to be one that uses invariance. You've probably already heard of loop invariance. In a similar way, in a proof, an invariant is just some property that's true throughout the entire process, in our case, the process of flipping chips. And the reason invariants are so useful is because they remain true no matter what method the person is using. So that means our proof will hold regardless of how they're choosing to flip these chips. So take a moment and try and think of some property that is invariant throughout this process. Alright, hopefully by playing around with this, you notice that whenever we flip a single chip, we either increase the number of red chips by 1 or we decrease the number of red chips by 1. And then this means that whenever we flip a single chip, this flips the parity of the total number of red chips. And parity is just a fancy word of the evenness or oddness. So we flip whether it was even or whether it was odd because we either increase or decrease the number of red chips. Since each move is 4 flips, that means that the parity of the total number of red chips remains the same after each move. If it started off at even, we flip 4 chips. So we flip once, twice, 3 times, 4 times, and we end up back at even, and the same for odd. So each time we make a move, which is flipping 4 chips, the parity always stays the same. So that means the parity of the number of red chips can never change. Whatever you started off with is what you're going to end up with. And we start off with 0 red chips since they're all blue, and this is even. So we know that we can never end up with 15,251 red chips because this is odd. We're always going to have an even number of red chips no matter what method they're using. So this is really the key here. No matter what order they choose to flip the chips, whether they're jumping around, whether they flip chips they've already flipped over before, we know that the parity remains the same, so you can never end up with an odd number of red chips. So you can never end up with 15,251 red chips. And now we have a good proof for this. After this whole process, it's really good to take some takeaways. So what did we learn throughout this proof? The first obvious one is we don't want to prove things for a particular method. So in order to do that, we should always be on the lookout for invariants. And lastly is that sometimes it helps to try and prove something stronger or more general. So in this proof, we didn't even use the fact that you could flip 4 consecutive chips. We just used the fact that you were flipping an even number of chips each time. So what we proved was actually more general and can work for slight modifications of this game. Say we were flipping 8 chips at a time or just 2 chips at a time, it would still work.